Hi, I'm Judy Cole, the Executive Vice President and CEO of the MIT Alumni Association, and I'm delighted to welcome you to this web production of the MIT Alumni Association.
Good afternoon, alumni. This is the MIT Faculty Forum Online. I'm Joe McGonigal, Director of Alumni Education. And this program is sponsored in part by MIT Professional Education. We're taking your questions live for our guests today, so please use the box next to the live stream to enter them, and we'll get to as many questions as possible. I'm joined by Justin Solomon, an ex-consortium career development assistant professor in MIT's Department of Electrical Engineering and Computer Science. Professor Solomon leads MIT's Geometric Data Processing Group, which studies problems in shape analysis, machine learning, and graphics from a geometric perspective. At MIT, Professor Solomon has taught shape analysis and introduction to computer graphics with Wojciech Matusek. Before coming to MIT, Solomon was an NSF Mathematical Sciences postdoctoral fellow in Princeton's program in applied and computational mathematics. He received a PhD in computer science from Stanford University, where he was also a lecturer for courses in graphics, differential geometry, and numerical methods. Before his graduate studies, Solomon was a member of Pixar's Tools Research Group. So Professor Solomon, thanks for joining us.
Thank you for having me.
Can you start by giving us an overview of some of the current research you're up to and your group is?
Absolutely, yeah. In fact, I have some slides here that I can show for you guys. Right. Oh, I see. Okay, right. Yeah, so to introduce myself a little bit, I guess we already got most of this data, but I'm a new professor in the Department of Electrical Engineering and Computer Science, which is part of the, or I am also part of the Computer Science and AI Laboratory. So at MIT, you know, there are departments and laboratories, and you get one of each at least. And I just finished my first year at MIT, I think as of about 1 week ago. So we're pretty new into this professor job and still learning a lot of things and working with students, and it's really a pleasure to be here. So for research-wise, I'm currently leading the Geometric Data Processing Group, which is in CSAIL and ECS. Our group has all kinds of different affiliations because we make use of all kinds of different ideas from mathematics, from computer science, from engineering, and so on. So in addition to being members of ECS and CSAIL, we also work a lot with people in machine learning. So CSAIL has a Systems That Learn initiative, as well as the Center for Computational Engineering, which takes PhD students not just in computer science, but also in mathematics, and aeroastro, mechanical engineering, with a focus on mathematical methods. So our research group, this Geometric Data Processing Group, oops, I'm flipping the slides on my laptop, but not here, is all about the theory and practice of geometry. And one of the really exciting things is that we're really right at the interface between exciting theoretical ideas in mathematics and optimization and computer science, and really practical applications everywhere from computer graphics and vision, which are the sort of obvious places for geometry, like deforming animated characters and using the space around your self-driving car to understand where obstacles are, to even more abstract places where geometry also appears, things like medical imaging, machine learning, and even sometimes things like supply chain. Understanding shortest paths and routing things along a roadmap is to me also a geometric problem. So I thought I'd highlight just a bunch of different images from different projects that we've worked on and are continuing to work on to show you guys the different themes that we have in our lab. And of course, I'm happy to share more information about any of this. So I'll just show a lot of pictures now and see what catches people's interest. So roughly, I'll divide into different themes here. So I apologize, it looks like we're cut off a little bit. Right, so one of the big problems that we study in our group is matching and correspondence. So here I have two different 3D brains. These are obtained using MRI. I think one is a postdoc and one is a graduate student in Stanford's psychology department. And the basic problem of correspondence is finding which points on one brain map to which points on another, right? And so this problem has so many different applications, not just medical imaging, maybe where I'm trying to transfer labels of segments and maybe different medical artifacts from one carefully studied object onto a new scan, but also in areas like computer graphics, right? If I want to interpolate between shapes, or computer vision, if I'm looking to identify key features or parts of a 3D or a 2D object, all of these are different critical problems that involve correspondence or really understanding the relationships between different 3D objects. And so we've studied this problem in all kinds of contexts, right? Everything from this computer graphics paper here where I'm given a cow, a duck, and a torus, and we ask the question, what is the shape in between? Now, obviously, this is kind of a corny example that's meant to illustrate what's going on in this paper rather than, I don't think anybody really wants this half cow, half torus object. But it goes to show you really the power of understanding how to match between different shapes, right? Because once we've found this basic correspondence, we can leverage that to make new creative tools. Or similarly, again, in medical imaging, we can use different types of assignment or matching tools to transfer labels or information from one subject to another. And in fact, we have some of the state-of-the-art tools for these correspondence problems. One of the really fun things about being in a mathematical research area like ours is after we develop a tool like this, I can throw it all kinds of different data and problems, right? So here you can see that we use the same correspondence tool to match two humans to each other, to this robot, to a point cloud, to the toilet sign outside of my office. And in each case, this is the same piece of software that's showing that, for example, the orange points all correspond to the top of the head and finding the knees and the feet and so on. In a very different application area, one theme of our research is an area of both mathematics and sort of optimization study that's called optimal transportation. So in optimal transport, I have distributions of supply and demand. So let's say that I'm running a gas station company and I have refineries and I have gas stations, right? And every gas station has some amount of demand, how many customers come in every day, how much gasoline they need. And every refinery produces some amount of gas. And our job is to match from supply to demand as efficiently as possible, right? I want to minimize the cost of shipping from one place to another. So this might not look like a geometry problem, but from my perspective, it definitely is. So in this case, the geometry is provided by the sort of the connections and the shortest paths in your road network, right? Things like traffic and so on determine how much fuel you're using to ship from supply to demand. And you want to do that as an optimal way as possible, right? And so we have a lot of different machinery for studying these problems. Even, for example, in the case where you have stochastic, like noisy and random data that's even changing over time, right? So maybe I'm driving a car along the road and all I want to do is, estimate sort of what's in front of me, where the obstacles are, and kind of maintain that information as I'm driving along. Then I need to deal with the fact that I've got tons of noise and the world is changing around me, right? And so these are really exciting applications right at the intersection of geometry and data. In yet another very different area of research, our lab does work with sort of engineers and the more classic versions of geometry problems that come up. So for instance, one big problem in very old school computational geometry is what we call meshing. So here I take a sphere and I want to divide it into little cube-like elements. And this is important for things like simulating fluids, gas and water and so on. Essentially, when you have a computational system for doing that, you need to take your smooth domain, like the area where you care about your gas that you're simulating, and divide it into little pieces where you're going to approximate it, right? And this is like a very low-level problem now instead of this high-level reasoning about shape. But it involves a lot of the same challenges, right? So we study problems like that, or surface parametrization, where I want to take this 3D cow and smash him into the plane, which artists really care about, right? Because typically, when I want to paint a texture onto the cow, the computer needs a way to store that texture, right? So you store the texture in an image, which is over this flat guy on the right-hand side, and then you display it on the 3D shape. To just continue in our big grab bag of different fun topics that we study in this geometric data processing group. Another one is shape analysis, right? So I have big databases of shape. And this is, people talk a lot about machine learning and big data and so on, and it's a very popular theme in computer science. But one place where it doesn't do as well is understanding 3D objects, right? So for example, I have maybe a database of humans in different poses or scans of tables and chairs, and I want to study those. Now, typically in machine learning or in statistics, right, I'm trying to come up with a label for like a data point, right? Some point in, with a bunch of different numbers associated. Like maybe I have a patient and I have his heart rate and his blood pressure and whatever. But it's actually not clear what a data point is for a 3D shape, right? So if I want to come up with a label for a table or a chair, this is a really weird type of data to be studying. And so our group really works on a lot of the different challenges in this world of shape analysis and looking for different features of 3D shapes. And this gets applied in all kinds of fun places. So for instance, in computer graphics here, I don't know if you can see on the slide, essentially in this paper earlier this year, we studied this problem of maybe I have a very basic shape. Like I'm willing to, I don't know if you've ever used CAD software, 3D modeling, whatever. It's ridiculously hard. You know, Microsoft Word revolutionized the way that we create documents, but nobody's done that for 3D shapes, right? And so maybe you go to the painstaking effort of modeling just a very simple chair, but now I want to put wrinkles and textures in it, right? And so we have machine learning systems that can figure out like, oh, you're modeling a chair, these are the different parts of your chair, and these are the types of wrinkles and the patterns that you see on it. Or in a different type of problem, maybe I have different humans and I'm trying to figure out their label, whether it's their identity, what pose they're in, and so on. So this is some combination of learning and shape, right? To highlight some other kind of fun efforts that happen in my group more broadly, we're involved in all kinds of different things in the community at MIT, in Boston more broadly. For instance, this summer I'm hosting, mostly organized by a mathematician at Tufts, but I'm the kind of the bad cop to her mathematical good cop, right? They need engineers too. We're holding a summer school on the geometry of redistricting and studying what does it mean to measure whether a districting plan for congressional voting, for example, is gerrymandered, and how do you come up with a mathematical tool that can measure this and optimize a districting plan when the new census data comes out. Our group hosted the New England Symposium on Computer Graphics, where we invited research groups and practitioners in computer graphics from all over the New England area, so not just MIT, but BU and Tufts and even farther out to come share their research. So really my goal here is to make MIT sort of the world center of both applied geometry and computer graphics research, and we're working very hard to do that, even though we're just 1 year in. In terms of teaching, currently I teach, in the fall I taught the Introduction to Computer Graphics class. I think that one's been around for a very long time. And then just this past spring, we taught a new course, which is 6838. I'm still getting used to, at MIT they have numbers for everything, which is new to me. But anyway, 6838 is a course entitled Shape Analysis.
And computer graphics is 6.837.
837. Yeah. So I'm lucky. And all the materials are online, actually. I encourage people to go take a look because it includes YouTube videos of all the lectures and slides and homework and all that kind of stuff, where really we were developing the theory and practice of shape at the same time. So we introduced the theory of differential geometry, how you can measure things like curvature and bending and stretching and so on, and sort of start with this idea of geometry in the small and eventually end up with geometry in the large. Like if I have a giant database of CAD models, all these different gears and tables and chairs that people have modeled, how can I navigate that in an intelligent way, do inference and draw conclusions about what's in my data set and so on. So anyway, I know this is a ridiculously huge grab bag, but roughly that's what my group is up to. And of course, it's so much fun talking to you guys because I know that the MIT alumni, have such a broad community of people that study problems all over these different applications. And I'm really hoping they reach out to me and come chat because, it's always such a pleasure to hear what people are doing and what they're excited about.
Well, we'll ask them to stump you today.
Yeah, oh
Good
gosh.
questions. Reminder to alumni to ask some good questions in the box to the right of your live stream today for Professor Solomon on computer graphics. You started your professional career after your PhD, at least, with writing a textbook on the subject, numerical algorithms. What prompts the writing of a textbook at the beginning of your academic
in
career?
fact, I was writing it during my PhD a little bit, which I guess is not too common. While I was at Stanford, which is where I got my PhD and undergrad and master's.
We don't hold that against you.
Yeah. While I was there, I taught a class that was entitled Numerical Methods for Graphics, Vision, and Robotics, I think, and some permutation of those words. And actually, really, this textbook came out of necessity. I taught this class a few times, and essentially, it's all about number crunching for these different applications. And typically, when you look at textbooks on numerical analysis, this is number crunching field, they kind of fall into two categories. There's like the yellow math textbook with theorem proof, theorem proof, theorem proof. And then over here, there's like this kind of prescriptive engineering, you want to solve a linear system of equations, so maybe here's this piece of software, we don't know what it does, but here's 50 different pieces of code that use it, and just to kind of convince you it's okay. And I wanted something in between where students at MIT and Stanford are grown-ups mathematically and engineering, and so they can handle the difficult stuff, but maybe they haven't taken the 10 math classes they need leading up to that point, right? So it was out of necessity that I was teaching all of these engineers stuff that I thought they could handle, but they needed more kind of grounding in application, right? And so that was the theme there.
Your preface says you we're going through a fundamental shift in the approach to modeling and problem solving. What's prompting that shift?
Yeah, it's really interesting to me. You know, for a little while, I would say maybe 5 or 10 years ago, when people thought about areas like numerical analysis in computer science, they kind of thought it was old school, like outdated or somehow, you know, relic of the past. But all of a sudden it's coming back, which is great for me. So, you know, essentially we live in a real valued world, right? The things around us are, you know, when we think about computers, you know, people typically talk about bits and bytes and, you know, ones and zeros and so on. But the things around us are measured in inches and feet and seconds and hours. And those don't fit into that nice framework, right? And so numerical analysis is this field that's all about how to develop computer algorithms that can deal with sort of, you know, items on the continuum, right? And so this is a huge theme in my area of geometry, right? I mean, you can take a shape and bend it and stretch it, and there's no kind of discrete behavior going on there. And really, this is just a total shift in the way that you think about using computers, right? When you talk about writing code and like sorting lists of numbers or clicking links on websites, just like, these are discrete events. But now, in this new world where you're talking about, you know, things like machine learning and computer graphics, a lot of these kind of application-driven fields, they're really worried about modeling the real world. And now all these other issues involving number crunching come back into play, right? And so to me, this requires a new way to think about how you design computer systems, right? The kinds of issues that come up when you're dealing with real numbers are just not the same. Like, you know, it's not just a question of efficiency, but, you know, approximation and, you know, how well are you approximating what's in the real world? How efficient do you get to that point and so on? All come into play rather than just this old school computer science approach of like, I want to count the number of operations I'm doing and make it as small as possible.
So some things that were old are new again.
Exactly.
And,
yeah, it all comes back, you know?
Yeah. I was intrigued by the title of a paper from 2009 in your CV, Programmers, Professors, and Parasites. It's called Credit and Co-Authorship in Computer Science. You suggest the establishment of a more consistent publishing standard for your field. Has the field listened 8 years later from that paper?
Yes and no. Yeah, computer science, I mean, to give a little context, computer science as a discipline is in a really weird place. So as everybody, you know, it's no secret that in academia people are always very worried about credit and making sure that they get their due for having put a lot of hard work into a research paper. And one of the ways that gets reflected is in the list of authors, right? And maybe if you're in engineering or you're outside of computer science, this isn't as familiar a story. But essentially when you read the list of names at the top of an academic research paper, it tells you a lot about who did what, right? Maybe the first guy was the main person doing all the work, the last person was the guy that gave the money, whatever. But the issue is that different fields have different standards for this. So for instance, if you read a theoretical math paper, almost always they just take the list of authors and they sort them by their last name, right? Whereas in biology, there's like these really complicated fights and negotiation and horse trading to go on about precisely what slot everybody goes
Who gets
into.
the marquee?
Exactly.
Right.
Yeah. And the problem that computer science gets, which is a blessing and a curse, is that we're so interdisciplinary, right? We're constantly collaborating with, you know, my group is a fun one because, like, on the one hand, we're talking to like artists and people doing medical equipment. On the other hand, we're talking to mathematicians. And then the problem is you get them all together, they have all these great ideas, and then you have to shake out how to, you know, give credit, right? And yeah, so to get, you know, to make a short story long, essentially the answer to your question is no, that we don't have a consistent standard. I would say different subfields in computer science have different standards for how to attribute credit. At least in my research group, the philosophy that I'm trying to pursue is that it really doesn't matter. We should all be friends, you know. And so we lead an open research group. If anybody that wants to contribute is welcome to show up and share their ideas, and we'll worry about credit. Never, you know. I will make sure my grad students are you know, getting everything they need for their career. But I don't think there's any reason to get in a fight.
Maybe it's unfair of me to go back 8 years in your CV, but
yeah,
nobody should
catch
have
me by surprise, you know.
Questions coming in from alumni. One real quick follow-up about the Tufts conference or the Tufts study.
Yeah, that became popular.
An alum asks, is it purely theoretical, or is there some hope of actual application to congressional district?
Yeah, no, it's not theoretical at all. Well, okay, sorry, that's a controversial statement. It is. There are a lot of theoretically minded people that will be helping organize and lead the discussion, but this is an event that's largely open to the public for the first couple of days. So the way we structured it, actually it became I guess we hit. I'll try not to touch on political stuff too much, but we hit it just the right time, and so this event got totally oversubscribed, which is exciting. So we ended up renting out the Somerville Theater rather than the auditorium at Tufts that we originally had, and we're going to have 3 days of public talks, which include not just theoreticians but also people that are involved in political science, people that do computation, to kind of understanding like how much of these theoretical ideas of can you measure if a districting plan is gerrymandered can actually be implemented in practice. To the really complicated legal ramifications of different systems for this. So we have 3 days of public talks, and then I think 2 or 3 days of sort of, they're not quite breakout sessions, they're like specialized tracks, right? So we have an educator track where we're gonna help high school and college instructors incorporate sort of lesson plans about why this is such a challenging and important problem, both on the mathematical side and on the civics side. And we have a track focusing on expert witnessing. How can you go about being an expert witness in a trial about gerrymandering? And then we have a third track, which is on GIS, like on global information systems. You know, how can you do this in practice and load census data and work with it?
So a decade from now, maybe a computer is telling us, sorry, your district looks to be gerrymandered, or it's got a poor gerrymandering score or something.
Right. Well, it's hard to know what's realistic, right? I'm not sure. It'll depend on the administration and a lot of different issues. Yeah. But I think for now, what we're trying to figure out is what is the right framework for simply arguing, you know, it's one thing to say, you know, I know when I see it, if you look at a district plan and say it's gerrymandered. It's another one to go to a courtroom and argue, like, this is clearly in violation of the Civil Rights Act, right? And it's that second question that we're really focused on. Like, how do you make a consistent and clear standard? And then how we go about implementing that is its own kind of technical, political challenge, I think.
So you've got a lot of projects going on.
Oh,
Our
yeah.
questions will be as scattered
that's great.
as that, and
Yeah.
we'll seem a little scatterbrained. But Alum asks, does any of your research look at optimal computer architectures for geometric processing?
That's a really excellent question. The short answer is no. I don't think that, in the sense that it's certainly not a problem we've studied in the past. You know, my background, I've kind of oscillated back and forth between math and computer science departments, so I can't say that I'm an expert in computer architecture, but I do think that it presents some really exciting challenges. So I know at MIT's partner laboratory, there's Lincoln Labs, you know, outside of the city a little bit. They've invented a particular hardware architecture for studying problems on graphs, right? Graphs are like, you know, connections of vertices that are connected by edges. So maybe like the social network is an example of a graph. And they've actually developed hardware for algorithms that kind of traverse and do statistics on graphs and so on. And we've been in some very preliminary conversations about like, well, typically on a computer, we store 3D surfaces as big collections of triangles, and this is a very structured graph. And a really cool question is, can we leverage these new developments in graph processing to help improve things like computer-aided design, computer vision, where you really have structured data, but the end goal is quite different. So anyway, you know, to answer this person's question, you know, I can't say that we've done it so far, but I'd love to talk about it.
Good,
you know.
Good. Have you tried these ideas, another alum asks, in 3D representation of buried geological structures? And it might be referring to one specific slide. I'm not sure.
Yeah, you know.
3D representation of buried geological structures.
Well, one example of this, there's a company called Schlumberger that studies. I don't know if you call it geological structures, but certainly
Oil
buried.
wells.
Right, exactly.
Yeah, right.
And we've done some talking about with them about how you, what is the proper way to, you know, take that buried structure and put it into a discrete structure that your computer can work with, and in their case, simulate, you know, the dynamics of the fluids underneath.
Well, a lot of shapes underground that we're curious about.
No, and CSAIL just last semester had a guest speaker who her tagline was that she's a space archaeologist, and she and I had a really fun conversation about, you know, I guess they sort of fly airplanes over different areas and are trying to detect where there might be a dig site that they haven't seen so far, and of course, I have a million ideas about like how to plug in some of these developments we have in shape analysis to help her you know, develop intelligent tools for finding these kind of non-obvious structures.
Talk more about your work in medical imaging and a recent paper was last year on Alzheimer's research.
Right.
Just curious.
Yeah, I mean we have So my background's in geometry. It's certainly not in working with patients. That's a special skill. But we have collaborators in worlds that work with data like MRI, in particular this diffusion MRI. So there's a gentleman, Franco Pistilli, in Indiana, who studies a problem called tractography. So your brain, from my very theoretical perspective, is roughly composed of two things, right? There's gray stuff on the outside and white stuff on the inside. And the white stuff is kind of foliated with little curves, which are these tracks of white matter that connect the different regions on your outside of your brain. And so the problem with tractography is all about tracing these different curves, right? And so in this research paper you're asking about, this was a collaborator at Stanford and this gentleman at Indiana. Essentially the question was, once we've solved this tractography problem, now we kind of have some estimate of the different tracks in your brain. Can you use that to detect like the different developmental stages of Alzheimer's, right? So the student that was working on that, she was applying machine learning tools to this data that had come out of diffusion MRI to some success. Right? It's still a very early work, but certainly I think medical imaging is a really exciting application for geometric tools. It makes a lot of sense, right? I mean, things like tumors and changes in brain structure and so on all manifest themselves as changes in the geometry of the structures in different anatomical parts of your body. And fine-grained tools for understanding those are still in their kind of infancy.
A lot of hope in what machine learning could do for diagnosis of other parts of the body too, besides the brain.
Oh, absolutely, yeah.
Problems.
And I'm so lucky that my office, for example, is right around the corner from Polina Gollan's office, who in her entire area of research is all on medical imaging. And so I'm really enjoying talking to members of her group that are studying different problems in that world. And then my other neighbor is Antonio Torrelva, who does computer vision. Anyway, it's a really fun place to be that way. Yeah.
Let's put you on the spot with another then. Well, please repeat the number for shape analysis. This student wants to find it on.
Oh, yeah. The number is 6838, or if you go to my research group's webpage, which is gdp.csail.mit.edu, and go to the teaching link, it should be the very first one there. And we've shared YouTube lectures minus one or two. You know what? I'm a new professor and funding is a little low, so my version of a filmed lecture is kind of a bootleg camera in the back of the room, but at least there's that, and at least except for two lectures where the camera broke. So most of the material is there.
Costs are coming down on MOOCs. And,
yeah, exactly. Maybe someday I'll come teach it in this classroom instead.
What about alumni, specifically of CSAIL's computer graphics group, which has been around for 20 years?
Yeah,
more,
easily.
Where are they these days, and what are they up to?
Oh, everywhere. I mean, MIT historically, along with Princeton, Cornell, Stanford, and lots of other places I'll probably offend by leaving out of my list, have the really early, the scientific development of computer graphics happened largely in research labs in academia rather than just in industry, right? And so the students from MIT's group are everywhere. I mean, we send a lot of them to industry jobs in places like Adobe or Adobe Research, Microsoft Research, whatever. Some of them are in faculty positions and postdocs. It's really everywhere, right? I mean, this is one of the top places, not just because of my group, but lots of people in graphics are here.
And talk about looking back at the research tools group at Pixar now, and do you just occasionally get little regrets? Oh, I wish I could be there with that kind of processing speed they have now. Or
they have render farms. They have these entire data centers. MIT has pretty good access to this kind of stuff, but it's different.
And talk about some of the work you did at Pixar.
Right, I was in the tools research group there for about 5 years. Yeah, it was on and off. I mean, it wasn't all full time. In fact, a lot of it was actually part-time undergrad and part-time Pixar, which is a weird combination. The tools research group at MIT at Pixar is a really unique place. I encourage anybody that wants to go into graphics research, go hang out there. Where essentially you're in one location where there's artists, there's engineers, and there's researchers, right? And so we would have artists that would come to our office with saying, hey, I just painted this look, and I'm wondering if you can somehow help us to create software that could animate this, beyond just this one frame. Everything from these very abstract problems to very concrete ones, right? I mean, a lot of the details in animated films that you don't think about require tons of CPU power, everything from rendering and drawing all the different textures and materials and objects in a scene to simulation, right? So one of the very first jobs I had at Pixar involved working with the cloth simulation pipeline, right? So I had this little clip from Ratatouille where Linguini, the chef, was running around the kitchen and his smock was flying every which way, and simulating that was quite a challenge because of the physics of the dynamics interacting with these animator-controlled, totally unrealistic, non-physical characters, right? And it's a really strange context that way.
It's not just insert apron.
Exactly. No, it's not that easy at all. And they have this huge staff dedicated to these, including people whose job is like virtual seamstress and things you don't think about really require a lot of work.
That's great. Go back to even before Stanford, Princeton. What drew you to computer graphics to begin with?
Oh gosh. I'll probably have a terrible midlife crisis someday because I remember in the 10th grade I had an internship at the Naval Research Lab working on 3D face recognition and using differential geometry on triangle meshes to find different features on your face, compare them to each other, and somehow I never really left that field. But that aside, to me, computer graphics and geometry and now kind of numerical analysis, these different areas, I've always kind of gone back and forth about am I excited about math or computers, and I decided I'd like to have it all, right? And there are a lot of different ways to do that, right? And in particular, math very roughly divides itself into kind of two different types of math, right? There's math where you're dealing with discrete objects, putting balls in buckets and counting and combinatorics. And then there's the type of math that involves smooth stuff, like real analysis and bending and stretching and geometry. And I decided I like that second one. But at the same time, I want to do computational stuff. And so when you take the intersection of those, that's kind of where you get as our research area.
And your students today, they want, what's drawing them into computer graphics, and is it a different reason than that?
Yeah, one of the really cool things is that our group has this huge diversity of backgrounds, both in terms of where the students have been and what they're excited about. So let's see here. My current two students, I have one that's been just excited about computer graphics, video games, whatever, forever. One that comes from the robotics world. Then incoming this fall, a little too successful with graduate admission. So I got a lot of grad students coming in, which is very exciting. And let's see, I have one who is in a math program in Cambridge, another one that's working on self-driving cars in Silicon Valley, one that's at Microsoft. And one of the really cool thing, at least the big experiment that I'm trying to run, is to get all these different people with all these different backgrounds and reasons that they're excited into one place and see what comes out. So yeah, I'm not sure there's just one place that people see.
Good. Other questions coming in. Talk more about supply chain and transportation. Are there domestic versus international markets that appeal to your interest in research more?
I would love to talk to people with more background in that. As a mathematician,
you had a slide of the U.S. map.
Right. Yeah. No, I mean, I think our algorithms are thankfully agnostic to political and geographic boundaries. But that aside, right. I mean, the way that we got into that world is a little bit circuitous. There's actually an area of mathematics called optimal transport, which dates back to the 16th century, I think. There's Maj was a mathematician who studied this, and then Kantorovich later got a Nobel Prize for some of these problems. And essentially it's all about how to match supply to demand in an efficient way, right? So how do you sort of, when you have lots of people asking for basically the same object in lots of different warehouses, how do you match one to the other? And so it's an abstract kind of algorithmic problem. This has been around forever, right? And it goes back to early days of linear programming and numerics and all this kind of stuff. But the twist that we have is that now the sort of scale of our data is so much larger, right? And we're dealing with road networks with millions of roads and supplies and demands that are distributed all along this very complicated network. And so I'm not answering this person's question in a very intelligent way other than to say, we're more focused on the algorithmic side. But something that really is important to me is talking to the people that are using this stuff. So for example, next week I'll be in Silicon Valley touring to all different companies. And one of my big goals while I'm there is essentially to meet with as many people in as many different application areas as possible to see okay, we're working with these mathematical models that have somehow been abstracted or capture some essence of a lot of problems that people are facing. Now I can come back and tell you how we solved it, and you can tell me why it doesn't actually solve your problem, right?
Yeah. And what are your needs?
Exactly, and that's, to me, I mean, that's where good research starts, right? I mean, there's so many really legitimate problems in the world that people care about. We don't need to be inventing new ones, you know, in some sense. Yeah.
We're hoping systems, I mean, maybe we're not hoping, but some hope that systems develop situational awareness, I read,
Right.
that they start to understand supply chain and demand
Yeah,
on their own. That
exactly.
It's not human interaction necessarily, right?
Right. You know, we're not trying to put people out of jobs. We're trying to have them more intelligent or interesting jobs.
That's
right.
right.
So,
Yes.
you know, there's no reason to have a human that's solving what's essentially a math problem by hand. You know, another example of this is in geometry, surface parameterization. You know, this cow that I flattened out onto the plane. I mean, currently what happens is an artist does that manually. I mean, essentially they're solving a differential geometry problem by hand, you know. So it's our job to relieve some of their pain, you know.
Right.
Yeah.
And you talk about how machine learning, you know, will never reach the singularity, or you know, computers. Alexa will never understand my sarcasm when I speak to it.
Yeah, Alexa doesn't even understand my, you know, how to turn my alarm off.
How many years until computers just get really good at recognizing a table and how to, you know, I mean, this is the autonomous driving question too, but,
Yeah.
before there is this, this turning point or tipping point into better understanding shape. Where are we in computers in general understanding shapes?
Well, so the field of computer vision has grown in leaps and bounds in the last 5 or 10 years, right? And now when it comes to solving problems over photographs, I mean, the state of the art is amazing for, you know, identifying people and objects and scenes and modifying them and doing all kinds of inference and study. It's so exciting, and you see that reflected in the academic world, right? I mean, these conferences like CVPR and so on, these computer vision oriented places are huge. So we're really good at images and photos that show up on like a nice little grid of pixels, right? Unfortunately for us, when we're talking about shape data, it's much more complicated, and the process has been a lot slower. I think this will be a big theme of research in the next 5 or 10 years, and I hope that you know, having a computer that's both cognizant of the world around it and eventually that can kind of assist in the creative process and you know, making new visions of the world around it are going to be some of the future that we see.
Probably plenty of national security applications.
Oh yeah, well, you know, that too.
Right, yeah. Of image recognition and aerial photos. Helping
Absolutely,
us better understand
and I
zones.
think organizations like DARPA and so on have a big hand in funding and getting that research to move forward.
Yeah. There was a question earlier at the beginning of the hour about the role of the research scientist, and CSAIL has its share of research scientists, and I don't expect you to speak for all of CSAIL, but that conceivably even the research scientist's job will be threatened by the machine as it gets better at doing analysis of data. Any thoughts on that?
I certainly hope that's not true.
And research scientists you work with that you would testify for.
Yeah. Well, whoever asked this question, I hope that they haven't had a poor experience in research, because, I mean, to me, I don't hire, you know, so my group currently doesn't have anybody with that particular title. We certainly have graduate students and postdocs, and in a sense, I'm a research scientist.
Right.
Our job isn't like to, and although I have spent plenty of time doing this, like, you know, clicking the eyes on 100 different photographs of people so that you can start training your system to recognize humans or something. I mean, that's not why I hire or value my research staff, right? It's for their creativity and thinking about new problems and new models and so on. And I mean, maybe someday computers, I think, will be a good assistant for that process. And there's a large part of my life that I spend doing very manual, you know, tasks that I would very gladly have my laptop, you know, do for me. But I'd say it'll be, at least my particular opinion is that research science is one of these very high value jobs that I think is going to be very hard to replace with a computer. I hope. We'll see.
We're just about out of time.
Oh.
Let me ask you one last question. You've just finished your first year at
Yes,
MIT. You've got 45 or 50 more of them, I'm sure.
I hope.
Tell me your hopes for year 2, and what most excites you about the work ahead.
Yeah, I mean, it's ridiculously exciting. My group right now is me, a postdoc, and 2 grad students. Starting in the fall, it'll be me, 2 postdocs, 6 grad students, and a visitor from Germany. And so we're expanding quite a bit. And of course, this is a challenge all over the board. Right? It's a challenge identifying good, exciting research projects for all of these people to do. It's a challenge for me. I gotta, my training is in math. I have to be a manager, and I have to. Unfortunately, this isn't the best time in the world for government funding, for example. Just to throw something out there as a big challenge in my life right now. So I have to, support these students and trying to isolate them a little bit from those kinds of issues, which are my problem, and really come up with the exciting mathematical, engineering, computational challenges that they're going to face, right? So what I would say is, year one was all about, figuring stuff out, right? How do I get to my classroom? What does a class at MIT look like? How do I, give a lecture that these students understand and give them the right amount of homework and all this kind of stuff. Now we've got the basics out of the way. Now we're going to start structuring and really understanding what does our lab look like, not just like a month from now or just like, pushing the inevitable away, but rather, taking a longer term view of what is the future of our research field and of teaching at MIT and how do we fit into that. Yeah.
Great. Good. Well, I want to thank you, Professor Solomon, for your time today.
Thank you.
If we didn't get to your questions, we'll pass all questions on to Professor Solomon.
Yeah, please email me.
This is, and you gave your website for your for your lab. But on behalf of the Alumni Association, thanks, and thanks for tuning in for another edition of MIT Alumni Faculty Forum. You'll be able to find the archive of this conversation along with past faculty talks on the MIT Alumni Association YouTube channel. Please join us next time for another edition of Faculty Forum Online. Thanks.
Thanks again for joining us. For more information on future MIT Alumni Association productions, please visit our website.